Okay, so factoring, we'll start with a review of factoring. And so we'll talk about actually four different factoring techniques. The first one that we'll review is the more basic, typical factoring with three terms. So if we need to solve this quadratic equation by factoring, what we would do is factor the left-hand side by finding two numbers that multiply to -21 and then add to +4. The two numbers that do that are +7 and -3. By factoring the expression on the left side this way, that tells us that we can set each of those factors equal to 0 and solve for x. We get x equals -7 and x equals 3. So this is the type of question you would have answered that you did answer back in 171. This is like 85% similar, or 85% the same to questions you'll be answering this week in 172 as well. Instead of having x's, though, we're going to have some trig function instead. So sine x or cosine x or whatever it is. But a comparable question for this week could be sine squared x plus 4 sine x minus 21 is 0. So it's identical in its structure. Again, instead of having x squared, we have sine squared. Instead of having x, we have sine. But everything else is the same. So what we could do to solve this equation in green is to factor it. It would factor in the same way, of course, sine x plus 7 times sine x minus 3. And then you could set each of those factors equal to 0. And continue solving those. We're not going to actually continue solving them. But the whole point that I'm trying to make is that the connection between the quadratic nature of the trig equation in green compared to the quadratic equation in black, and the relationship or the similarities between how they factor. So everything we're going to talk about factoring is going to be in the context of a 171 type question. But for a lot of them, when I'll make a comparison to the 172 comparable equation you could see for the week. But questions there about how we factored the one in black or how it relates to the one in green. Okay. Another cool, yeah, thanks. Another factoring technique is if we have four terms, we can use factoring by grouping. So how that works is we would group the first two terms together and then the second two terms together and remove a common factor from each group. So from the group in red, we have a common factor of x squared. From the group in blue, we have a common factor of -4. And so what that tells us is that this equation factors into, the outsides go together, x squared minus 4. And then the common factor, x plus 3, we're going to recopy it just one time. But it ultimately factors into x squared minus 4 times x plus 3. The x squared minus 4 is similar to one of the factoring rules we reviewed last week, if you were here for that. X squared minus 4 is the difference of two squares. It can factor further into x plus 2 times x minus 2. And so now that it's fully factored, what we can do is set each factor equal to 0 to solve for x. Again, same sort of ideas to what we did with the earlier one. We just have that additional difference of two squares we can factor. To solve it for x, though, we would get x equals -2, x equals 2, and x equals -3. A comparable type of question you could see this week in 172 is sine to the third x plus 3 sine squared x minus 4 sine x minus 12 is equal to 0. Again, just replacing the x's with sine x's, or any other trig function. I keep using sines, but it could be cosine or tangent or secant. Literally any of the trig functions would be totally fine. And since the original equation in black is identical in structure to the trig equation in green, ultimately what that means is that the one in green can factor in the same sort of way too. Sine x plus 2 times sine x minus 2 times sine x plus 3. Taking that a couple steps further, that would tell us that sine x equals negative 2, sine x equals 2, and sine x equals negative 3. You're not going to solve these from this point forward, but we're only a couple of steps away from actually getting the answer to the trig equation. And almost everything we've done, there's necessarily no new skills from 172 involved. All the factoring we did and setting factors equal to 0, all that's from 171. So even though it's, solving trig equations, like I said at the beginning, I think I said like 85% of the stuff you'll do is really similar to stuff you've already done. That extra 15%, of course, is super important, but a lot of this is similar to what you did in 171. But questions about that one and factoring by grouping? Okay, I'll scoot that one up. The third factoring technique you could encounter for the week, or just in general that you could encounter, is just taking out a common factor. So if there's 3 terms, we can use the more, the typical factoring that we did for the first example. If there's 4 terms, we can try factoring by grouping. If there's only 2 terms, the best, and we could factor using some of the special cases from last week. I'll jot those down real quick. Last week, we reviewed difference of 2 squares. We reviewed difference of cubes. And we reviewed sum of cubes. So if you have 2 terms, checking to see if one of these 3 special cases applies is a good idea. If not, if none of them apply, the best you can really do is to take out a common factor. And so none of those 3 cases apply here. And so really the best we can do is to take out a common factor of x. And that leaves us, factoring out the x leaves us with the square root of 3x plus 3 in the parentheses. And then again, as always, we can set each of those factors equal to 0 and solve for x. X equals 0 is done. For the second factor, we can subtract 3 from both sides and then divide everything by the square root of 3. What are you doing, buddy? I'm going to scoot this over to the right for just a second so I can show the comparable type of trig equation when we did that for the earlier two. So I'll use a different function now just to show that it doesn't matter. But the square root of 3 times tangent squared plus 3 tangent x equals 0. That equation in green has the exact same structure as the one in black, which means it factors the exact same way. So we would have tangent x times the square root of 3 tangent x plus 3. That would tell us, again, just kind of following the exact same steps, that tangent x equals 0 and tangent x equals negative 3 over the square root of 3. But all of those, everything we did in black originally has a really strong connection to the system equation. You can see this week in 172. Those were the ones in green. questions about anything we wrote or anything we did there? Just a review of factoring.
I have a question. So you're sharing your screen, right?
Yeah. I'll stop sharing it. You joined after I started sharing it, and it didn't dawn on me that normally if that happens, you don't get to see what's being shared
There we
earlier.
go. All
Sorry.
right.
I
No,
saw when
this
you
is-
came in. Hey Gerard, I saw when you came in. I didn't dawn on me to start sharing again.
Oh no, it's all right. Thank you very much.
Yeah. So in addition to these factoring techniques, we can use what's called the AC method to factor. We might use the AC method if we need to factor something where the leading coefficient is not 1. So that would be something like 3x squared minus 14x plus 8. So when the leading coefficient's not 1, it just kind of complicates might be a good word, but it makes the factoring process a little trickier. And so one of your options to factor when the leading coefficient is not 1, you can factor using, like you can guess and check. I'm not a huge fan of that. I'm not a good guesser. I've always felt like anytime I was using that approach, I was just kind of spinning my tires, not really making much progress some of the time. I like to feel like I'm making progress when I'm doing work and when I'm thinking about these kinds of questions. So I've always been a fan of the AC method. At least once I learned that how it worked, I was always a fan of it. And so we're going to review that. For the AC method, how that works is we actually multiply the A value times the C value. In this case, that's 24. What we do with that is look for factors of 24 that add to that middle term, that B term. The two numbers we can use are negative 12x and negative 12 and negative 2. What we do with this is we separate that negative 14x into negative 12x minus 2x. I'm going to keep the 3x squared the same and the 8 the same. But what this does, so we're essentially done with the AC, the new stuff here. There's more to do. It's not factored, obviously, but the next step of this is kind of a repeat of one of our earlier ideas. But what we've done is we took this thing with 3 terms. We multiplied A times C. We got factors of that number that allowed us to split up that B term to create an equation with 4 terms. But what this does, what we can now do is factor this by grouping. So this is what I meant a second ago, that the rest of the process is kind of a repeat of an earlier idea. So for factoring by grouping, in the first group, we can take out a common factor of 3x. From the second group, we can take out a common factor of negative 2. And so that tells us that ultimately the original equation, the original stuff on the left side, factors into 3x minus 2 times x minus 4. Again, the stuff on the outside of the parentheses gets its own group. The common factor in the parentheses, it gets its own factor at the bottom too. And just like before with factoring with grouping, we would then set each factor equal to 0 to solve for x. We would get 3x equals 2, so x equals 2/3, and x equals 4. A comparable question you could see this week in 172 would be 3, let's do cosine. I don't think we've used that one yet. 3 cosine squared x minus 14 cosine x plus 8 is 0. And again, since the original equation in black, the quadratic one, is identical in structure to the trig one that's in green, going through the entire process would tell us that cosine x equals 2/3 or cosine x equals 4. And again, this isn't solved. We're not, the point of what we're doing isn't to solve these equations, but I'm pointing out that if we, by applying the exact same ideas from the equation in black to the equation in green, we'd obviously have to end with the same results there because the structures of the equations are identical. Again, I'm not, the equation over here in green, we haven't solved it. We're not finished. There's another few steps left in actually solving that. Our point's not to solve it. My point is to make the connection with the factoring and show how they're related, though. Questions there? And when I'm putting the arrow, what I'm saying is that if we, all of these steps would be exactly the same and lead to the same conclusion. It's kind of an ugly arrow, but all these steps would lead us to the same conclusion. All right, I'm gonna scoot that up and I'll recopy one more and actually give you some time to try this one. Oops. 2x squared. I'll give you a second to try using the AC method here and see if you can factor it. So again, just kind of as a reminder, the first step is to multiply a times c and then find factors of that number that allow you to separate the middle term. I'll give you a minute or two to try that and then we'll chat about it. So factoring by grouping, we multiply a times c, that gives us the -6 we already mentioned. But we then need to find two numbers that multiply to -6 and add to -5. The two numbers that do that are -6 and +1. What that tells us then is that we can separate that -5x term into -6x plus 1x. The first term and the last term stay exactly the same. But now we have 4 terms and can factor by grouping. From the first group in blue, the common factor is 2x. From the group in green, the common factor is 1. There's not actually a common factor, so except there's not an x with that 3, sorry. It's just -3 at the end. Shoot. So we get x -3 for the factor in green there. And ultimately what that tells us is that the original equation in black factors into 2x plus 1 times x minus 3. And so we could then set each factor equal to 0 to solve for x. We will get 2x equals -1, and so x equals -1/2, or x equals 3. A comparable equation from this week in 172 would be 2 secant squared, we'll use another function, 2 secant squared x minus 5 secant x minus 3 is 0. And ultimately, like again, and what's always been the trend, since the equation in green and the equation in black are identical in structure, the middle steps, for what we have in green, there's going to be some secants involved, but it's going to factor the exact same way, which ultimately means that the conclusions would be the same. Secant x equals -1/2 or secant x equals 3. And again, there's a few more steps involved actually solving the equation. We're not talking about those, only talking about the factoring approach. But questions about anything we did there with the AC method again? Okay. Then our next factoring stop is we're going to talk about something called substitution. And we might consider using substitution when the thing we need to factor is a little tricky or confusing or cumbersome, or any other words related to that. But what substitution does is it allows us to rewrite the equation into something that may make a little more sense. It is something that maybe looks a little more familiar. And so what am I talking about? So here we need to factor x to the 4th minus 10x squared plus 16. Well, we haven't talked at all about factoring something that has an exponent of 4, but we did spend a whole lot of time talking about factoring things that have exponents of 2. And so what if we could rewrite this as something that has an exponent of 2 instead? We can do that by making a substitution. I'm going to make a substitution u equals x raised to some power. The power we need is always going to be half of this first exponent there. Half of 4 is 2. So we're going to make the substitution. We're going to say, hey, everywhere this equation has an x squared, I'm going to put a u. But what that allows us to do is to rewrite the equation in black as u squared minus 10u plus 16. And so the equation in black maybe was a little tricky, maybe was a little just a little much to kind of think about and to just orient ourselves with, but perhaps rewriting it as what we've got here in red makes it a little easier to work with. Because the thing in red is something like, it's really similar to what we've looked at a ton of times today and maybe a ton of other times in life. Because what's in red is quadratic. That factors into u and u, and then we need two numbers that multiply to 16 and add to -10. The two numbers that do that are -8 and -2. From here, as we did with the earlier ones, we can then set each factor equal to 0 and solve for x. We get u equals 8 and u equals 2. If you use substitution, at some point, you have to undo the substitution, right? The original equation, the instructions would have said solve the equation for x, which doesn't mean solve for u. It literally means solve for x. At the moment, we solved for u. So if you make a substitution, you've at some point got to undo the substitution by replacing the u's with whatever they substituted in place of. In our case, that's x squared. So that would be x squared equals 8 and x squared equals 2. To solve for x, we can square root both sides here. And that tells us that x equals plus or minus square root of 8, and x equals plus or minus the square root of 2. questions there. So substitution is not something, this isn't a, you're not obligated to use substitution. It's just more of a tool that you can kind of pull out of your bag and use it in the event that you are maybe struggling to factor something, but that perhaps rewriting it would make it a lot easier to factor. And normally when that would come up in 172 is actually you can use substitution to in fact remove the trig equation, remove the trig function from the equation, and just look at something involving u's maybe instead. I'll show you what I mean by that in a second. We'll look at one of those. Before we do one, I'm going to copy one more here. X to the 6th minus 3x to the 3rd plus 2 is 0. So I'm going to give you a moment, a couple minutes to try factoring this using substitution. Remember, we want to turn this into something, the original equation here in black is not quadratic. It would be helpful for us if it were quadratic, as we've, factoring quadratic equations is something we've done a lot of. So let's use a substitution to turn this or to rewrite this as a quadratic equation. Remember, what we do is divide that first exponent by 2. The 6 becomes a 3. So the substitution is going to be x to the 3rd. I'll give you a second to try making that substitution and then factoring there. And ultimately, unsubstituting it to solve for x. Because don't forget, we always have to unsubstitute.
No question. I have to leave. I thought I was gonna be able to sit through the whole thing, but I have to work. But I'll be here next week. Is it you do these at 3 on Mondays? Is that a normal time or thing?
1:30 is the first one, and then the one at 3. There's 2 options: 1:30 p.m. on Monday, and then 3 p.m. on Monday. Okay. So 1:30 maybe would work better. You can sign up for that one too.
It might work better. Okay. All right. Thank you. See you then.
But it's George, is going to be recorded, or it is being recorded, so you can at least access it later in Teams. This one anyway, since you're leaving, you can still access it.
Okay. It'll just be on as part of the Teams.
No, it's going to be in your chat. So your chat history in Teams off to the left.
Okay.
It says you no longer have access to the chat. I think I'm going to need to add you back. I'm not sure. I saw that message pop up a few minutes ago. I'll add you to the chat, and so you will then have access to the chat, and you can see the recording from the chat there.
All right.
If you don't see it, you can send me a message, and we'll figure out what went wrong and get you access.
Okay. Thank you very much.
Sure. Enjoy work.
Bye-bye.
Bye. So the substitution we'll use here is x to the 3rd. What that allows us to do is to rewrite the original equation as u squared minus 3u plus 2. And the whole reason why you may consider doing this is because factoring u squared minus 3u plus 2 might seem a little easier to you, on a personal level than factoring u to the 6 minus 3x, or sorry, x to the 6 minus 3x to the 3rd plus 2. Maybe it doesn't seem simpler. If it's not simpler, like I said, you don't have to do this. It's just an option to maybe make something that's a little more challenging to see how it factors and look a little easier. So this factors with the u's, it factors into u minus 2, u minus 1, which tells us that u minus 2 is 0 and u minus 1 is 0. And so u is 2 and u is 1. Anytime we use substitution, we always have to undo that, right, and solve for actually the variable we were given. So that would tell us that x to the 3rd equals 2 and x to the 3rd equals 1, which means x is the cube root of 2 and x is the cube root, or sorry, the cube root of 1, which is 1. I didn't mean to do that. Questions about that one?
So it's not plus or minus the cubed root because it just ends up being positive at the end, right?
The plus and minus only comes up with even roots, so square root, fourth root, sixth root, but we don't put the plus or minus with odd roots.
Okay.
And so when might you use substitution in 172? You might use substitution if you needed to factor something like, or you need to solve an equation sine squared x minus sine x minus 2 equals 0. Maybe factoring this with all of the trig functions and the signs, maybe, maybe there's just a whole lot going on, and it's, at least at the beginning of the week when you're first starting to factor these, maybe there's just too many things, too many moving parts, and you just, struggle to see what step to take. Well, we can use a substitution to simplify what we're looking at. Let's use the substitution u equals sine x. That would allow us to rewrite this equation as u squared minus u minus 2 equals 0. And then we could factor that. It factors into u minus 2, u plus 1. And setting the factors equal to 0, we can solve for u. We would get u equals 2 and u equals negative 1. As always, if we use substitution, you do have to undo that, which in our case would mean sine x equals 2 and sine x equals negative 1. But what we did in this middle period, these steps, is we essentially solved the trig equation, but we weren't being bogged down by all the trig terms. We solved the trig, we're mostly solved. There's still a couple more steps at this point. There's still a few more things you'll have to do to ultimately solve it for x. But we got really close to solving this and never actually had to worry ourselves with the trig nature of it because we made a substitution to kind of remove that concern. So that's ultimately where you might use substitution. To substitute in something that allows the trig equation to look a little easier and maybe, in fact, be a little easier to solve. Questions about that connection? Okay, questions about factoring at all? Because next we're going to kind of make an abrupt change of course and talk about modeling with trig equations. Okay. All right, so modeling with trig equations. This is a review. What we're going to do now is a review of a topic you looked at 2 or 3 weeks ago, maybe 4 weeks ago. I forget exactly when it was, but you looked at it earlier this semester. It was covered on test 1. So the topic I'm talking about is when you are given the graph of a trig function, you are asked to come up with an equation of its graph. Right, so generically what that meant is you needed to write an equation that looked like y equals a cosine b x minus c plus d. Something like this. Your teacher maybe wrote the equation, this generic equation, a little differently. This is at least the generic equation WebAssign used in any of its help tips or help me solve this or whatever it calls those things. This is the generic equation WebAssign used. So that's why I'm writing it this way here. But the task for this topic back then was to figure out the values of A, B, C, and D. A and D actually had equations we could use to calculate them. A is max minus min over 2. D is max plus min over 2. B also had an equation. It's 2 pi divided by the period. C was the only one that was just didn't have an equation, maybe a little more annoying to to work with that, but C was the starting point of a sine or cosine cycle. And so just to talk about these characteristics on the graph a little bit, the max and the min, those are the largest values and the smallest values, right? Max is up here. The min would be down here. The period, that's the distance from one maximum to one maximum. Or from one minimum to one minimum. I'm kind of out of room for that. But from one minimum to one minimum, that's also a period. To get the C value, the starting point of a sine or cosine cycle, you would need to consider the generic sine and cosine graphs. So generically, the graph of y equals sine x of one cycle of that function looks like this. Generically, y equals cosine x, one cycle of that graph looks like this. And so to figure out the C value in our question, or for our equation, we would need to match up, look along the graph we have and find a basic repeating unit of the sine graph or a basic repeating unit of the cosine graph. So that was way back what we did a few weeks ago. Ultimately, though, the huge takeaway is that we needed to calculate the A, B, C, and D values. And that's exactly what we're doing this week in 172 as well. It's a repeat. Literally, there's no new skills. It's a repeat of what we did from a few weeks ago, only now it's in the context of a word problem instead of in the context of a graph. But it's the exact same stuff. So what I'm going to do is put a question in the chat. It's a screenshot. And this is one of the lab manual questions from this week. This is the exact type of question you're going to see this week. What it says is that the Bay of Fundy in Nova Scotia has the highest tides in the world. In one 12-hour period, the water starts at mean sea level, rises to 21 feet above, drops to 21 feet below, and then returns to mean sea level. Ultimately, we need to find an equation that models these tides. And so what that means, it's describing for us everything that a graph would describe. It's just in words. And maybe that, and perhaps honestly, that might make it a little easier. I'm not sure that it could be true that it's, instead of picking out the information on a graph, the information is already written for us in words. What I'm going to do, though, I'm always a proponent of this. I like to draw pictures or diagrams to represent word problems. I think I know for me that's really helpful. If you don't need to draw the pictures, if you can visualize everything that's going on, no obligation to draw a picture, but I'm going to draw one here. So what we're told is that in one 12-hour period, the tide starts at mean sea level, goes up to 21 feet above, down to 21 feet below, and then back to mean sea level. So all of this takes 12 hours. The highest tide is at 21 feet above sea level. The lowest tide is at 21 feet below sea level. Our task is to write an equation that represents these tides. So that means we need to write a function by figuring out A, B, C, and D. Before we actually talk about A, B, C, and D, I'm going to point out, I've already written the sine function here. We could write a sine or a cosine function. I've already written sine. The reason is, look at our graph and look at the generic sine graph. They're exactly the same. the generic sine graph starts at its midline value, goes up, down, and back up. That's exactly what's happening in this question here. If for some reason the question said that the tide starts at 21 feet above sea level, decreases to 21 feet below sea level, and then rises back to 21 feet above sea level, that would have matched a cosine cycle. So it's a really good idea to identify, is the scenario described, does it match a cosine cycle or does it match a sine cycle? Sometimes it may not match either, so in that case you would pick either one you want. But in the event that the function actually tells you, in the event that context actually says, hey, a sine cycle is what we should use, or hey, a cosine function is what we should use, then you should use the proper function. And in our case, that's the sine function. All right. So, but using all this information, we can figure out the values of A, B, C, and D. A is the maximum minus the minimum over 2. 21 plus 21 is 42. Divide that by 2 to get 21. D is max plus min over 2. 21 minus 21 is 0. 0 over 2 is 0. And B is 2 pi divided by the period. The period is 12 hours. That's how long it takes to go through this complete cycle. 2 pi over 12 is pi over 6. So we're mostly there. Y equals A sine B x minus, we're going to come back to C in a second, and then plus D, which is 0. C, that's the starting point of the cycle. So we've already identified that we're going to use a sine cycle. The time when that cycle starts is the C value we need to put here. But that sine cycle starts at a time of 0. Right? It's the beginning of the scenario. So C is 0 for our sine cycle, for our sine function. And so this is our equation with all the components incorporated. The zeros, of course, we don't need to write those, so I'm going to next drop those. But this is ultimately the cycle we would create, or the function we would write. Questions there?
So is C always 0 for sine? That's just a rule?
No. It's so the C value is the starting point of the cycle. So let's say at 2 a.m. So between 2 a.m. and what would it be? 12 hours later, 2 p.m. Let's say that this was the tides. That it started between the information we had went from 2 a.m. to 2 p.m. In this case, C would be 2 because that's the time the sine cycle starts. Does that make sense or no?
Yep, that makes sense.
Okay, so if you're writing a sine cycle, the C value is, in this case, the time that cycle begins. But not always 0, no. Hazani, I think you were trying to ask something too? Maybe not.
No, I wasn't.
Oh, sorry. All right. I thought I heard you come on. If the question had said that, the tide starts at its maximum, we would have written a cosine cycle, but in that case, the C value would have still been 0 because this is the starting point of the cosine cycle at a time of 0. Same thing from when we shifted the other one. If the tides went from 4 a.m. to 4 p.m. Whoops. And it was a cosine cycle, maximum to maximum, then fine, we would have a C value of 4 for the cosine cycle there. But it all has to do with the time. In this case, the time, it doesn't always have to be time. For most of the problems, it will be time, but it has to do with the time that the cycle itself begins. So on that post, that covers the stuff that I've got planned. It's always the goal to leave about 30 minutes of time for you to ask questions about anything you've been working on from this week, last week, anything about today. So I put our second survey in the chat. I know I asked you to do 2 of these a week, and I appreciate you hanging in there with me and doing them both. But if you could complete this new survey, it's a post survey, I would definitely appreciate it. It's the same questions you already answered, but now having heard everything that we talked about, you can answer them maybe with a different kind of outlook. But if you could answer those before you leave, that'd be really great. But for the rest of our time, I will answer any questions that you have. Can be, like I said, about anything we talked about today, anything you've been working on for your class. Literally anything related to the class is a fair question to ask, and I will answer however many questions we can get in the next 35 minutes. But you're free to go when you're ready. If you don't have questions, of course, no obligation to stay and sit here. But if you do have questions, I'm happy to talk about them.
So I had a question from a WebAssign homework. It's one question that I have left that am like 99% sure that I have right, but it keeps telling me I'm wrong. So okay. I was wondering if you could help with that.
I can. What? Can you?
It's on the 7.5 homework. It's number 7, but I can just read it all out to you if you want, or take a screenshot.
Well, it might help if you would send a screenshot. Just if you've already done the work, I might just seeing what you've already typed your answers in, I think, right? Is that what you're saying?
Yeah.
If you'll send me if you'll put that screenshot, don't put it in the chat here. I don't want anybody to get upset if we're like kind of sharing answers. But can you send it to me in a private message real quick?
Yeah, I should be able to do that.
I'll send you a message just to start a chat. But if you'll send it to me, I just sent you the message. If you'll send it to me there, I can look over it, and if it's a semantics thing, I can tell you that. But I don't want anybody to look back at our chat and misunderstand why you're sending answers of questions in here. And Hazani, of course, if you have anything you want to ask while we're waiting for Grant's picture, go ahead. I know last week was identities, and generally that's so the answers are expected to be in radians. So looking at okay, so you eventually made it to that. You don't need the plus 2 pi k business. The question, what plus 2 pi k does is list all of the solutions. This question only wants the solutions between 0 and 2 pi. So if your work is correct, and I'm not saying that it is, this is just my preliminary look at it. You would only type in the answers would only be the angles you have, not the plus 2 pi k part. Does that make sense what I'm saying?
So I checked my factoring on like a website that I use that helps with like equations and stuff, and my factoring was right. And it was the same process that I did for all the other problems that I got right. And I even put those in degrees and it still accepted them. So this one is just confusing.
Can you tell me how it factors? I don't want to do it, but if you already know it's right, we can start from that.
Yeah. So basically it factored down to x equals negative 1/6. And then x equals 1/2. But yeah, the sign is, or the x is sine x. So for sine of x negative 1/6, that doesn't exist. So I just didn't include it.
It exists.
It does?
Yeah. So sine x equals 1/2 at pi/6 and 5 pi/6. And these are the two that you've got.
Right.
What I'm saying, so my first thing that I said was that I didn't actually know it would take the answers if you put them in degrees, but don't do that because that's not what it's asking for, and that might just be a bad habit to develop. If it asks for answers between 0 and 2 pi, it means in radians.
Right.
If you were completing my test and did put answers in degrees when I asked for radians, you would. I mean, not get full credit because that's not following the instructions. I'm actually surprised to hear that WebAssign takes that. I didn't know that it would do that. So your answer should be in radians because that's what it asks. But also what I'm saying is you don't need the plus 2 pi k. This is only if you're providing all of the solutions.
Yeah, I really only put that in there as like
Just as
last ditch.
Okay.
I couldn't figure it out.
I see. Yeah, so it doesn't want, so don't do that. So that needs to come out. But so let's talk about, so you said sine x equals -6 doesn't exist, but it does exist. It's not on the unit circle. It's not one of the special angles, but it exists. So in sine x equals -6, in which two quadrants is sine negative? Can you tell me that?
Yeah, 1 second. Well, it'd be the bottom two, so 3 and 4.
3 and 4. What you've got to do is you're going to need a calculator. The reason you need a calculator is the reason you're permitted, I suppose, with the question is because at the top the instructions say to round to 4 decimal places. And so what we've got to do, sine x equals 6 equals -1/6. So let's do inverse sine of -1/6. Oh, I need to be in radian mode. So inverse sine of -1/6, make sure you're in radian mode. I was not, and I got a funny looking answer. The inverse sine of -1/6 gives us back an angle of -0.16744800792 radians. Do you agree? Is that what you got from your calculator?
Yeah, I got the same thing.
What that's telling us is that this angle down here in quadrant 4 is -0. I'm just going to use 0.16 because I don't want to write all those numbers, or 0.17. -0.17 radians. The question, which is not in 0 to 2 pi, remember we need all of our answers in 0 to 2 pi. So -0.17 is not in 0 to 2 pi. But what we can do is find the angle coterminal to -0.17 that is in 0 to 2 pi. How we can do that is by adding 2 pi to -0.16, blah, 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 blah. So if we add 2 pi to that, we get that x equals 6.1157. So I'm going to write that in a different color. So that's this angle, that green one there. Do you agree with, does that make sense?
Yeah, I think I did something slightly like that, but I put it in degrees. So that's probably why.
I'm seeing your second answer up there, and I thought, I mean, it looked like you could have done something like this. You saw the 30 and the 150, that's fine.
Yeah, I think I got it in degrees, and then I added 360 or something to get a coterminal.
Yeah, maybe. So don't forget, so we need two answers here, because you told me the sign is negative in quadrant 3 and in 4. So we also need an answer in quadrant 4. What's interesting about the two is that their reference angles are exactly the same. So the reference angle here is 0.17 radians. So from pi radians, if we add 0.17 radians, the 0.16 blah, 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 we get the second answer, which is 3.3090. But the thing about the question is that it's asking you to round your answers to 4 decimal places, which means these two are fine, the blue one and the green one, but you also have to round these, the original two as well. I know they're convenient to use pi over 6 and 5 pi over 6, but if those are the answers you intend, they also have to be rounded because that's what the homework is expecting.
So for the second answer, is it not pi plus negative 0.16?
No, it's not the negative. So we're adding the reference angle. We're not adding the angle, the inverse sine value. We're adding. So we need to know this angle that I'm highlighting here in blue. To get to that angle, we can rotate all the way around to pi radians and then an additional 0.17. That's the reason we need to add it.
So where did the 0.17 come from again?
I rounded the 0.16. I didn't want to write all of those decimal values.
So we don't keep the negative in there?
No, we're not using the negative at all. We're using the reference angle. Reference angles are always positive acute angles. A reference angle is the positive acute angle made between the terminal side of your angle and the x-axis. So if we're in quadrant 3, this is a reference angle, and it's got to be positive. Reference angles are never stated as negative. It came from the negative 0.167, but what the negatives told us originally was that, hey, this negative angle actually is a solution, negative 0.167. But if that's the actual angle, but if we're talking about the reference angle, we have to ignore the negative sign if we're going to talk about in terms of a reference angle. Negative 0.17, that's the actual angle, but I need the reference angle. And that has to be positive.